forgot to hit this. Okay, so if the system isn't liking the degrees of freedom that come out of your t interval or your 2samp t int function in the calculator, then use the minimum of this degrees of freedom to compute your t critical value and or your margin of error, and then it will accept it. So far, only one person has said they've had a problem with it not accepting the interval they got out of 2samp t int. That even if it's not accepting the margin of error, it went ahead and accepted that interval. But one guy said, no, it did not mean I had to do it the way the formula in the book said. So just word of warning tonight when you're doing the homework, if you haven't already been certified on this, when you're doing the homework, if you hit a problem, go back and do it this way. All right? If you still can't get it to work, then take a screenshot and email it to me. Right? If I don't see it in time, I might see it in time, especially if the Royals go into extra innings again. Right? But if I don't see it in time, then I'll give back the 5% penalty that you'll get if you don't get it done by midnight. Right? So if it's a rounding issue because of your calculator, I don't want that to get in the way of things. So just don't panic. Just take a screenshot, say, here's what I entered, it said it's wrong, and I'll give you the credit. Got it? Everybody happy? Any questions about that, about this stuff? No? Okay, so today we are going to do section 9.3, which is similar but a very important difference in that it's two sample means problem, but those two samples are now paired. Now, we talked about this last time. Independent samples versus paired samples, right? Give me an example of paired samples. What would cause data to be dependent or paired? It's okay, I can wait. What kind of data would have one sample of numbers that can be paired with another sample of numbers? Megan? Good. Yeah. So smoking or not, but it was done in married couples. So each male could be paired with a female. Those are dependent samples. Another common example is a pre-test, post-test kind of thing, right? Anytime you measure the same subject or the same object twice, those two measurements can be paired because they came from the same subject, right? So, most of the time when we have to decide if they're independent samples or dependent samples, we'll do it based on whether did I measure the same subject twice or are they completely different subjects, right? So today is all about what do we do if it's paired data. Okay, so for paired data, well, before I get into that, we're going to do an activity today, right? To illustrate this topic. So we're going to generate some real data, right? So
Field trip.
Yeah, field trip. At the beginning of the semester, I had you collect pulses on people, right? And one of the things I was adamant about was they need to be seated for at least 5 minutes before you take the pulse, right? And the reason for that is because some people will tell you that there's a difference in pulse measured when you're standing up versus when you're sitting down. Do you think that's true?
Yes.
Yes.
Okay.
Maybe.
Most people believe that. How much of a difference?
Not much.
Yeah?
You mean like if they just stand up, like from sitting?
Right. If I measure your pulse while you're standing up, is that different than when you're sitting?
Yes.
Yes.
Probably really small.
It's
Okay.
probably quite a bit. That's why doctors make you wait so long in the office.
Okay. Well, let's find out.
Can't you know?
Let's find out how big of a difference it is, or if there's a difference at all. All right? let's do an experiment. Got 20 people in here that I can use as test subjects. So let's design an experiment. Remember back in chapter whatever, we talked about design of studies, and we did observational studies and experiments and all that kind of stuff. Let's design an experiment. Well, I say experiment. Will this be an experiment or an observational study?
Experiment. Oh, true.
Well, what's the
It's an experiment. 'cause
what's the hallmark of an experiment? What has to be true for it to be called an experiment?
You change something. Change the
You,
variable.
you change the treatment, right? The researcher decides who gets what's treatment. Are we going to do that here? Yeah, probably
Yeah.
so.
Standing up.
Right? Standing up versus sitting down. So this will be an experiment. So design an experiment. What do you think we should do? Say it loud.
Everybody take their pulse sitting down.
Everybody take their pulse sitting down? Well, then where do I get standing observations?
We stand up. And then do it again.
Split us in half.
Split, okay, so split the group in half, and half of you stand up, and half of you sit down?
But
You don't have the
comparing
amount.
them necessarily. Like, shouldn't you take your pulse sitting down and standing up? That way you can compare your two.
Okay. Both of those designs are valid, right? They're both valid. One, divide the class in half, and half sits down and half stands up. That's a valid experiment. You'll get valid results. But the idea is, can you do better? And so you said, no, shouldn't we measure everybody both ways, pair their data? What does that do for us? What's the advantage of that?
Then you're not comparing like one person to another person on either side of the room that are like completely different in like male or female body shape and like
Okay?
the rest
Lurking
equal.
variables or confounding variables. That's what you're talking about, right? My last class when we just did this, the discussion was a little more, somebody volunteered right at the very beginning. Well, when we were trying to pick a design, they said, well, what I would do is I would divide by sex, I would divide by who's an athlete, who's not an athlete, I would divide, and so they're thinking of all these lurking variables. Well, the problem with that, dividing into those small groups, is pretty soon you got so many things that you only have one person in a group, right? But a design where you measure the same person twice accomplishes that, right? So Adam's an athlete. What do we think about heart rate in athletes?
They're lower.
Typically lower, right? Typically lower. And so if Adam got randomized to be in the study and is in one group and not the other group, then that would be extra variability. But when I measure him in both conditions, just take the difference, then the fact that he has a really low heart rate, he'll probably have it in both conditions low, and the difference might be equivalent to everybody else's difference. So a lot of the variability goes away. You get a more efficient design. And what's that design called, where you measure each subject on each treatment just in some randomized order? What? You don't remember the name of this design? Have I mentioned?
The test is cumulative.
The test is
It's called a crossover design. You remember that? And I remember the example we talked about with crossover design was an allergy medication that I had worked on. And you study them for 1 week, and then you switch them to the other treatment, right? Crossover designs will only work if whatever it is you're measuring will return to baseline when you take the treatment away. That should happen with heart rate. If I stand you up and measure your heart rate, and then I let you sit back down, your heart rate should go back down to where it was before. I shouldn't permanently have ruined you, right? So crossover design is a good design. So that's what we're going to do. And I'm going to take my calculator, and I'm going to randomly assign, let's see, we've got, what I'm going to do is I'm going to point at each of you and give you a number. This is your subject number. Right? So you have to remember your number. Got it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Everybody remember their number? Okay? Now, last class I used only 8 people in my sample. But I think in this one we're just going to use everybody. Right? 8 people turned out to not quite be enough to show what I wanted to show. Usually it is, but I had some weirdos in there. So what I'm going to do is I'm going to take my calculator. I'm not going to randomly select you since I'm going to use you all. You already are my sample of 22 people. But what I'm going to do is randomly assign you to a sequence of treatments. So you're either going to be a stand-up, sit-down person, or you're going to be a sit-down, stand-up person. Got it? Right? So over here, we're going to have 2 sequences. The sit, stand, wait, it's the other way. I'm trying to remember how I set it up on the computer in a minute. So I think I did sit, stand, sit first, and then sit, stand. Okay? So what I'm going to do is, there's 22 of you. I'm going to draw 11 numbers randomly between 1 and 22, and you'll be the first group. The rest of you will be the second group. Got it? So here we go. If you want to play along, you won't get the same numbers I get, but remember it's the math button, then you go over to PRB for probability, and then there's a rand-int function, random integer. And then I put 1, 22 to give me a random number between 1 and 22. All right? So you know I'm not cheating, it truly is random. Trent's going to watch?
18.
18. So who's 18?
That's me now.
You already forgot your
I
number.
thought I was 17.
So this is 18. Next one is 11. You're going to trust me, right? So, okay. 11. 18 again, so we just hit a new one. 14. 1. 4. 21. 22. 1, 2, 3, 4, 5, 6, 7. 22 again. 17. I need more room. 8. Keep track for me. I'm losing track of how many I've done. 13. Is that 11? That's 10. Number 1. We've got number 5. All right? Everybody know who they are? Okay. Now, I need a volunteer to come and be the data entry person on the computer. Steve went. So,
I'll do it.
okay, you can do it. If he wouldn't have volunteered under pressure, I would have randomly chosen somebody to do it. But so what I'm going to do, since he's up here, scroll down till we get to a table right there. That table. And you may have to add some rows to this. And you can ignore the stand-sit thing. Well, no, you can't either. Sit down. I'm going to have to do it. I designed this for 8 people. Now I got 11. All right, so I got to add some rows to it. But so that should be enough. 1, 2, 4, 6, 8, 10, 11. Yeah, good. We'll just do it on the board. Heck of it. Right? So everybody else, read off to me the numbers that I'm missing out of this list, and we'll put them over here. So 2's not on there.
3,
3,
6, 9, 10,
12.
12,
13. Oh, wait, never mind.
13's on there.
15.
15,
16.
no, 6.
16.
Okay.
16,
17.
17,
Never mind.
18 are on here. 19, 20. Is that 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? So these are my sit standards. Okay? So if you're in the stand sit group, stand up. If you're in the other group,
Stacy.
sit down.
I feel like my
Find your pulse. Everybody find your pulse.
I didn't.
I'm waiting for everybody to nod at me like, okay, I got it. I don't want to start. And what I'm going to do is I'm going to give you a go, then a stop, and it'll last for 30 seconds. And I want you to count your pulse for those 30 seconds. Ready, go. Stop. Okay, you can sit back down. Double your number, and then you're gonna call them out. All right? So the stand sit group, number 18, what was your standing heart rate?
78.
78. Number 11,
82.
82. 14,
84.
84. 1,
77.
77. Shouldn't be an odd number.
Sorry. I lost my pulse halfway through it.
So this is, in clinical trial lingo, this is what we call a not protocol correct subject, right? Or a dropout. So what did you?
Let's just stick with 78.
Okay. I'm going to put an asterisk by that. Is there something wrong with this data, right? But this is real life. This is what happens. There's always something weird happening. Number 4, 76. Number 21,
74.
74. 22,
72. 36. 80.
80. Number 8,
66.
number 13,
56.
56. Number 5, couldn't hear you.
72.
72. Okay? Now the sit column over here are the people that stayed seated. So number 2,
72.
72. Number 3,
78.
78. Number 6,
I got 56.
what?
56.
56. Okay? 7,
76.
9,
70.
70. Number 10,
72.
72. Number 12,
64.
64. Number 15,
52.
couldn't hear you.
52.
52. Okay. 16,
76.
76. 19,
11.
70, and 20.
62.
62. Okay? Now, if that's all we did, we could put these into L1, put these into L2. We've got independent samples, right? These are different subjects than these are. We could do a 2-samp T-int on this just like we did last time, okay? If we have time, we'll go back and do that, probably with my calculator. But if we did that, we would be throwing away half our data, the half we get here, right? So the crossover design will help us get rid of some of that extra variability, extra noise. So if you were in the sit-stand group, stand stand up. Now technically, in order to measure the people who were standing before, they need to be
sitting for 5 minutes.
They had to be seated for 5 minutes. And I didn't look at my watch to see if 5 minutes went by, but we're going to go ahead and call it good, because we'll run out of time if we wait for another 5 minutes. So everybody needs to find their pulse. Boy, you count better this time. Everybody got it? Just go. Stop. Okay, double your number and read them off to me. If you don't learn anything else today, you'll at least learn how long 30 seconds can be. Doesn't it seem like it just takes forever when you're standing there waiting? Okay, so everybody got their number doubled? Number 18.
72.
72. Number 11. 80. Oh, and by the way, as we're doing this, start entering the stands into L1 and the sits into L2. Right?
Oh, it stands.
Stands into L1.
All like both columns of
Both
stand.
columns.
Okay.
So this column first, and then the one that we're going to get here will go below it. Got it? So, number 14.
78.
78. Number 1.
74.
74. Number 4.
64.
Number 21.
64.
64. Number 22.
68.
68. Number 17.
72.
72. Number 8.
60.
60. Number 13.
56.
56. Number 5.
65.
60 what?
64.
Guess what you just got? An asterisk. Are you confident with that 64? Okay, now over here, the standing people. Number 2,
78.
number 3,
88.
number 6,
64.
number 7,
84.
number 9,
72.
number 10,
84.
number 12,
78.
78, number 15,
56.
56, number 16,
80.
80, number 19,
74.
74, and number 20,
78.
78. Okay. So now while you're doing that, I'm going to do in my head the differences. And I'm going to do the differences taking stand minus sit. It doesn't matter which way you do the subtraction, but once you pick a way, then you have to make all your conclusions based on that. Right? And I'll have you check my math here.
Do we need to put all the sits in L2?
Yeah, and put all the sits into L2, but make sure they're paired together. So this 78 needs to be next to this 72, and this 82 next to this 80, and so on. So don't mix them up. Everybody see what I mean by that?
You just said.
78 minus 64. 4, wow. That's 14.
I really got rid. It's me.
And 78 minus 62, I can't do that one in my head. That's
I lost track of my
16. Okay, has everybody got their data in L1 and L2?
No.
Yep.
Okay, I'll let you catch up. Now what I want you to do, when you have stands in L1 and sits in L2, go ahead, question? Which one you pointing at? This one?
Down one.
Oh, number 4. 76 minus 64 should be 12. You're right. Thank you. Okay? But you don't have to enter the differences because your calculator will do it for you automatically. Go over to L3. Arrow up till the L3 is highlighted at the top and press enter. And your cursor should jump down to the bottom. Did it do that? Now down there, type L1 minus L2. So you need second function 1, then a minus sign, second function number 2. Press enter, and it should do the pairwise differences and drop them all into L3. The numbers you have then in L3 should be these 11 numbers and then these 11 numbers. All right? Now, if you find that one of mine is wrong, you can holler. I don't know that it's important as long as you have the right numbers.
You're right.
Yep. Go up, highlight the L3 at the top, press enter, and the cursor goes to the bottom. Now type L1 minus L2, and then enter again. Okay, everybody got it? So what have we done here? We had 2 samples, a sample of standing heart rates and a sample of sitting heart rates. But we've reduced that problem from a 2-sample problem to a 1-sample of differences problem. And that's the whole strategy for paired means problems, is you reduce it. Since they are paired, you take the difference within each pair and you get 1 sample. So everything else you've already learned how to do. You just do a 1-sample t interval on the differences. Okay? So the point estimate, let me start out. Mu sub d is the population mean difference. Okay? So then the point estimate of that would be what? What's the best estimate that you have for the population mean difference? What did I tell you the other day? Whenever I ask you that, what's your best estimate? The mean of the sample. And it's the mean of the differences, right? And so we use a little different notation here. It's D with the bar over it. D for difference, bar for sample mean. So it's the sample mean difference, okay? Now, S sub D is the standard deviation of the differences. I forgot to write up here, mean diff, standard deviation of the diff, right? So we can form the confidence interval as D bar plus or minus a t critical value times SD over the square root of n. It's exactly the same as you did before, only now we have the little sub D and everything to indicate it's on the differences. But it's a 1-sample problem, 1 sample of differences. Okay? So now go to the stat button and then calc and then 1 var stats and do 1 var stats on L3. And tell me what D bar is.
7.
What? 7 even?
There's
No decimal?
No.
Wow. Okay? And then I'm going to leave a blank for this t critical value. We'll figure that out in a second. What's the standard deviation of the differences? 4.08, give me one more place. 2. Divided by the square root of what?
22.
22. We had 22 differences. Okay? So n is 22. Now, t critical value. Where do we get t critical value? Okay? So our degrees of freedom is n minus 1. We said n was 22, so we need 21 degrees of freedom and the inverse t function. Right? Or the t table in the back of the book. So, 95% confidence. So I said the other day, if I ever forget to say, assume 95%. So we're going to do 95% confidence. So give me the inverse t. Do you remember what to enter into inverse t?
0.95 for the area.
Is it 0.95?
0.025.
0.025 or 0.975. Either one of those will work, but it's half of alpha. And alpha is 1 minus c. So 0.025 with 21 degrees of freedom. What's the t critical value you get there?
2.08.
Okay, go ahead and give me 3 places.
That's
It's 80? Okay, gotcha. Okay, so we'll fill that in here. 2.080 for the t critical value. Okay, so this part is called the what? When I multiply those two things together, what is that called? Margin of error. Right? So we denote that with a capital E. So on the homework, when they say compute the margin of error, that's what you're doing. Okay? So go ahead and give me the confidence interval. Does anybody have the left bound or the lower bound yet?
5.18. I mean,
It's 19, I think.
yeah.
I
Two
did it
decimal places is plenty. 5.19.
I did it with the additional 8. Additional 7.
Okay. And what's the upper bound?
8.810.
8.810. Okay. So what's the interpretation of that interval?
We are 95% sure that the mean of the difference is somewhere between 5.1 and 8.8.
Okay. We are 95% confident that the mean difference between standing heart rate and sitting heart rate is somewhere between 5.19 beats a minute and 8.81 beats a minute. Right? So somewhere between 5 to 9 beats per minute difference when you stand up. Your heart rate speeds up by that much. Right? That's what that's telling us. Okay, now, before I go to the next little... No, I want to finish it. Does this interval provide evidence that there is a difference? Yeah, why? Because it does not include 0. Since 0 is excluded, we would say 0 is not a plausible value for the mean difference. The plausible values are in the interval, so the only values in the interval are between 5.19 and 8.81. Those are the only values that we think are plausible for the mean difference. Right? Now it's interesting, I will compare your class to my last class where I only used 8 observations. They had a D bar of 3 point something. So not quite as big as yours. Yours was 7. Right? Theirs was about 3 something. So that is abnormally small. Most semesters it's between 6 and about 10, somewhere in there. Right? You got closer to the 6, but they also, I only used 8 subjects. So their interval went negative 1.3 up to like 5.6.
That's 95%.
And they were 95% confident, right? So it's a wider interval than yours, right? Yours is only, what, 3.6 is the total width of that interval. Theirs is more like 6.6. Right, it's actually about 7. Right, so their interval's wider. Why is their interval wider?
Because you use less subjects.
Because I have less subjects. N on the bottom of a fraction. If this n is bigger, the standard error is smaller, so the margin of error is smaller, so the interval's narrower. Right? So they have a better, you have a better estimate of the truth than they do. Right? Both are valid, but yours is more precise. You got a tighter interval because you use 22 people instead of 8 people. Now, back to your calculator, push stat, go over to tests, and do T interval. Now, you can either select stats and enter the stats that we read off, or you can just say data, and your data is in which list? L3. And do a 95% confidence interval. You should get this same interval, only it may round slightly different because the calculator is going to keep more decimal places of accuracy on all these things. What does that function give you?
The same thing. It doesn't round any different.
Okay. It just gave you more decimal places. Okay? So you get exactly that. Awesome. Okay? So, let's have you do one on your own. One whole experiment. No. Okay, here is an example out of the book. It says, in a CPR class, students are given a pre-test at the beginning of the class to determine their initial knowledge of CPR, then a post-test at the end of the class. Educational researchers are interested in whether the class increases a student's knowledge of CPR. You would hope it would, right? Now, construct a 95% confidence interval for the mean increase in CPR test scores. Now, there is a key word here, increase. So you have to do your subtraction in the correct direction so that you get increase. The direction of subtraction really is arbitrary. You can do either way you want. But when you make your conclusions, you have to realize, well, which way did I do my subtraction, so what would an increase mean? If they increase, the post-test should be higher than the pre-test. So if I do my subtraction post minus pre, I should get positive numbers. Right? So, figure that out. Now, before we flip the page here and show the data, on the next test, there's not going to be a flashing neon sign that says, here comes a dependent samples problem. You've got to figure out several things. The first thing you've got to figure out is this a means problem or is this a proportions problem? Which is it? Quit staring at me, which is it?
Me.
Is this means or proportions? Means. How do you know? Because it says means. It's really that easy. Now, sometimes it might not use the word mean, but it might say average. Right? It's going to say one of those two things. If not, at least you can say, well, it's a quantitative variable. Right? Pre-test, post-test score. It's a number. It's not a category like do they smoke or not. Proportions problems are categorical variables. What proportion of people are in this category? Right? So it's a means problem. Second question, is it one sample or is it two samples?
Two samples of the same people.
It's two samples, a pre-test and a post-test, but, like you said, they are the same people, therefore they are independent or dependent samples. Dependent samples. Right? So you got those three questions you're going to ask. Right? And I recommend on your next cheat sheet, you set it up like that. It's like a flow chart. Means or proportions, or a tree diagram, right? Means, proportions. Oh, it's means. Is it one sample or two? Oh, it's two. Are those two samples dependent or independent? Oh, they're dependent. And then down there you say, here's what you do, right? Here's the formulas. Here's the function on the calculator. All that. So set it up so that you can go through the thought process to figure out what kind of problem it is. That's where most points are missed on the next test and on the final, is throwing the wrong hammer at the nail. Right? You got a whole bunch of tools now to use. You got to figure out, well, which one fits this problem. That's what's hard.
When is the next test?
I don't know. Soon. It's right before Thanksgiving. So here's the data. You work this problem. I want a confidence interval for the mean increase in scores. I'm going to set this down so that it stays pointed at the screen. I think the numbers are showing in there. You arrow up to the L3 is highlighted, and you push enter, and it drops down here. Now you type in L1 minus L2. Enter, there. Okay. So now you can do the same thing, but with this data. Oops, sorry. Trying to get it down so it's definitely in the screen. Does anybody need help? As soon as you get the data entered, take the difference and put it into L3, and then answer the question, find the point estimate, and all that. Yeah, somebody is saying the name or something. You know what I think I'm going to do? It looks like you had some lists get deleted somewhere along the line. So I'm going to do this setup. L1 and L2 are in the right order, and then we go back to L3, that's it. Now is the problem. You already got an interval? Yep, that is right. I wouldn't be answering. Now practice writing down your interpretation of it and what it's telling you.
The 1 bar snap. Because that's actually X bar.
Okay, so you're going all the way out, doing it all by hand, using the point, which is fine, but remember, you can use key interval.
Did you do the other one?
Yeah, I think so, right? I think it's the same.
It is.
But I prefer the possibilities.
Okay, there's 10 observations, so you got 20 scores to enter. Then you put the differences into L3, and which direction did you do your subtraction? Did you do it so you got positive numbers or so you got negative numbers?
Positive.
Okay. If you did it so you got positive numbers, then that's the easiest because it asks about mean increase. But if you get negatives, that's fine. There's no reason to re-enter the data or do anything different. You can just interpret it in the correct direction and you'll be fine. Okay. So find the point estimate. The point estimate is D bar, and D bar is equal to what? 16.8. Okay. SD is what? The standard deviation of those differences.
3.6147.
I heard too many numbers at once.
2.615.
3.
3.615. Did I hear that right?
Mm-hmm.
Okay. And N is
10.
10. A common mistake, not real common, but every once in a while somebody on the next test, they'll ask for N and they'll say, oh, there's 20, because there's 20 numbers in it. But then it's the number of pairs, not the number of numbers. Right? Number of subjects that got tested. And each got tested twice, so 10. right? So you could do out the formula for the confidence interval like I had a minute ago, or you could just bail out and go to T interval. And do you select data or stats? Easiest thing to do is select data. You could also select stats and enter these three numbers and you get the same answer. Right? Possibly with a little bit of round off error, but select data and then tell it the data is in L3. The confidence limit is, did I ever say? 95%. And what interval do you get?
14.214 and 19.386.
Okay? But you're not done. Because you have to interpret that.
We are
What does that mean?
95% confident that the difference mean is between those two numbers
Good.
for the test scores.
Yeah, we are 95% confident that the mean, and they use the word increase, so I'm going to use the word increase, the mean increase in test scores, or at least use the word difference, right? The mean difference is somewhere between 14 points better and 19 points better than they did on the pretest.
What was the margin of error?
The margin of error you can't get from doing it this way, but you could take 19.386, subtract 16.8, and that'd be the margin of error. But if you need more decimal places of accuracy, like the Hawk system sometimes, the margin of error, E, is the t critical value times SD over the square root of N. That's the margin of error. Okay? All right, we're out of time, so we will see you then. See you Friday. Good luck.
No sign.